We are working now at part 3 of this problem, where we're calculating numbers of newborn babies, and specifically we're asked, how many babies would you expect to weigh more than 6 pounds? As before, I'm going to start by drawing a standard normal distribution to help assist in visualizing the problem. So we have a standard normal distribution curve, the mean being 6.4, and the standard deviation of 2. So that means the first standard deviation away occurs at 8.4 pounds, the second at 10.4, and on the left, the first standard deviation occurs at 4.4, and the second at 2.4. These are our baby's newborn weights. Now we want to know how many babies we expect to weigh more than 6 pounds this time. So we can now locate using the standard deviations as our reference point where 6 pounds would be located. And I see that 6 pounds falls right here, just left of the mean. And we're looking for the number of babies that weigh more than 6 pounds, or that we would expect to weigh more than 6 pounds. And that's equivalent to answering the question of what percentage of babies fall in this blue region, or what is the area under the curve in this region. So that's what we're trying to find. Because 6 pounds does not lie on a straight standard deviation, we need to calculate the z-score corresponding to 6 pounds, and then use that z-score and our table of values to get an area. Calculating our z-score, we see that z equals, our x value is 6, our mean is 6.4, and our standard deviation is 2. So we have 6 minus 6.4, or negative 0.4 divided by 2. And negative 0.4 divided by 2 is actually negative 0.2, or 20. That's our z value, or our z-score that corresponds to 6 pounds, negative 0.2 or 20. We're now going to look on our chart and determine the area that corresponds to this z-score. But notice when we go, our z value is negative, and that's because it's talking about the area left of the mean. Specifically, when we use our chart, we're going to be looking at the area just left of the mean that falls in this red band. So our z-score is going to help us obtain this area. So let's look at our chart. We are looking for a z-score equal to negative 0.20, and that would be negative 0.20, and we ignore the negative, correct? We just look at the positive value or the absolute value. And so it looks to me like that area is 0.07926. Going back, we're going to label this as 0.07926, and that's what comes directly from that z table. This is the area under the normal distribution curve, or if we like, the probability that a baby falls in this area here between 6 pounds and 6.4 pounds. But we want the entire area to the right of 6 pounds. We also need to worry about all of this part here. But we happen to know, because this is my mean right in the middle, that this area to the right of the curve is just 50%, or 0.5. So to get the total area to the right of 6 pounds, or our z-score negative 0.20, we would simply take the value we obtained from the table, 0.07926, and add it to half of the area under the curve, 0.50, and that's going to give us our total, 0.57926. This right here represents the area under the curve to the right of 6 pounds. If we want to look at it as a percentage, that would be 57.926%, we would expect falling to the right of that 6 pounds as far as newborn babies go. Our last step now is to actually calculate that number of newborn babies. So we have to go back and take our 800 and multiply it times 57.926%. So I'm going to take 800 and multiply it times 0.57926. And that gives me approximately 463.408. Of course, we can't take fractions of babies, so we're going to round that up, and we get 464 babies one would expect to have a weight greater than 6 pounds at birth from this group. Cool, one more to go.